Okay, so we're going to start figuring out where electrons are located and the layers that they get put into. This is really helpful for figuring out what's on the outside. And really, this is all we care about. So what's on the outside of the atoms, because that's where all the interesting chemistry happens. So we're going to worry about core electrons, those that are buried, just so that we know they're buried. And then we're going to worry about the valence electrons, the ones on the outside. Those are the ones that we're interested in. So let's go back to the Bohr model for a minute. So the Bohr model is really helpful for thinking about these things. The Bohr model says for something like I don't know, an atom that is going to have a nucleus, and surrounding that nucleus there are going to be areas where we can find electrons. We'll call these energy levels. So there's an energy level 1 here. There's another place where we can find electrons. We'll call it energy level 2, and so on. There are going to be these various energy levels. So we draw this as a concentric ring, but really recognize this just a geographic location where we can find electrons. So I have these series of energy levels, and the problem is that electrons have a negative charge. So I put a negative charge here. I can't get too many more negative charges this close to the nucleus, right? I'm going to think about this. It's like having a pyramid-shaped hotel, right? Everybody wants to be at the top with the best view, but I only have a couple of rooms there. So my next layer down, I have more space, which is going to be true here. And as I get further down in my pyramid-shaped hotel, I have more places where people can stay. Same idea is going to be true for electrons. So I'm going to worry about trying to pack electrons in as close to the nucleus as I can, and then worry about which ones are left on the outside. And again, it's the ones on the outside that we're going to worry about that make the most difference. So you don't have to know too much about this, but I do need you to be able to figure this out by looking at the periodic table. So I encourage you to go to ptable.com. So it's an online periodic table. And you can learn all sorts of stuff. So here I'm gonna click on nitrogen or phosphorus. Why not phosphorus? So it's telling me a bunch of information here. So hopefully you recognize that number 15 in the upper left-hand corner is telling me that phosphorus has 15 protons inside its nucleus. And that big number, the 30.974, is telling me that on average there are 30.974 protons and neutrons that are found inside the nucleus. There's also some other information here that they're telling me about electrons. So the neutral atom is going to have just as many electrons as protons. So that 15 tells me the number of protons in the nucleus. It also tells me in a regular neutral atom, so not charged overall, in a neutral atom there will be 15 electrons. Lastly, you'll notice that there's a list of numbers in the upper right-hand corner of the box around phosphorus. This is the 285, so that is my electron configuration. So that's telling me at the layer closest to the nucleus, I can get 2 electrons, and the layer second away, I'll find 8 electrons, and the outermost layer, I will find 5 electrons present there. Okay. So what this is saying is that the outermost electrons is 5, and the innermost is 2. So you may notice, so if I go to nitrogen, innermost electrons in 2, the next layer has 5. I go to phosphorus, innermost is 2, then 8, then 5 is my outermost. I go to arsenic, I have 2, then 8, then 18, then 5. So you may notice the commonality here, right? So a group or column on the periodic table is put there because they behave similarly to each other, and the reason they behave similarly to each other is because they have the same number of outermost electrons. We'll call those valence electrons. I mean, here's another way of looking at this. So we were looking at nitrogen. We're just looking at this layer. So this is showing the Bohr model, and don't be confused into thinking that electrons are blue balls that orbit in sequence around something. They don't behave that way at all. So it's just a representation of things. They're waves, they're funky, but this is just one way of thinking about it. So but notice what's happening here. So I have my nitrogen, which has these 2 innermost electrons. We don't care about those. And it's got these 5 on the outside. Those are the ones we care about. I have phosphorus, which is going to have these 2 innermost, and then 8, and then these 5 on the outside. And arsenic, which is going to have a bunch more inner layers, but on the outside, it's going to have these 5 electrons. So what I need to be able to do is have a few ways of finding this information, representing this information, and then we'll start taking advantage of that when we start making ions out of these. We'll start adding or subtracting electrons to find things that are more stable than things in their neutral state. So We're going to have a handful of ways of representing this. So this model is 1, so we'll call this the Bohr model. So this is how I want to draw a Bohr model. If I was asked to do that, I want to draw circles and put dots around there. Really, I don't care about the innermost electrons. What I care about are the outermost electrons, and these are valence electrons. So we're going to have a way of showing the valence electrons for things. This is going to be called a Lewis dot diagram, which is going to allow us to show just the outermost electrons that are present. So this is a handy little application here, so I can look at something. I don't know. I can go to let's go to this one. So notice here I've clicked on the second group. The second group has 2 outermost electrons for beryllium. Oh look, magnesium also has 2 outermost electrons. Oh look, calcium also has 2. So anyway, you can see the idea that things in the same group, the same vertical column, they're going to have the same number of valence electrons. So this is what I need you to be able to recognize. So I'm going to ask you to be able to pull out things. So my electron configuration is what I'm going to call the placing of the electrons. So in arsenic, and let's write down the electron configuration of arsenic. So arsenic has this 2, 8, 18, and 5. Let me show you what that looks like, and I'm going to ask you to go through and be able to identify these arsenic. So it says number 33. I'm going to ask you to identify the electron configuration, be able to identify the number of valence electrons, and then be able to show that by drawing a Lewis dot diagram. So let me walk you through doing those for a few examples. So arsenic is one of those. Let me pull up my other diagram. So let's do arsenic. I don't know, let's do magnesium. So magnesium, element number 12, meaning it has 12 protons and 12 electrons. And those 12 electrons are arranged in 2, 8, 2. I don't know, let's go to bromine. Bromine has 35 electrons. Good grief, I don't want to draw all of those. It has 2, 8, 18, and 7. And I don't know, we could take a look at neon. So neon has 10 electrons and 2, 8. Okay, let me draw out some of these things I'm going to ask you to be able to do in just a minute. So let's see, we go here. So, nope, focus. There it is. Okay. So arsenic. So this is, when I looked at arsenic on the periodic table, I saw this information amongst other things. So this is what I'm going to ask you to do. I'm going to say energy level. So what is my electron configuration? My electron configuration, right? So at energy level 1, I'm going to have 2 electrons closest to the nucleus. Energy level 2, I'm going to have 8 electrons. Energy level 3, I get 18 electrons. Right. I have a total of 33, so the remaining electrons are all left in energy level 4, and that's going to be 5 electrons. So the number of valence electrons is going to be 5. That's the number of electrons in the outermost energy level. And this is the really thing that's interesting. That's the number of electrons that are going to be involved with doing stuff that we care about for really the rest of chemistry class. So here's how I want to draw a Lewis dot structure. So Lewis dot structure, I'm going to put the element name in the middle, and I'm going to put the valence electrons. For each valence electron, I'm going to put a single dot, and I'm going to work my way around each side first. So it's 1, 2, 3, 4, and then I'm going to start doubling them up and then stop when I get to the number of valence electrons. So this is 5 valence electrons that are going to be here for arsenic. So this is the Lewis dot structure for arsenic, which is a really handy way for us to show what's happening in an element. And we're going to expand upon this when we start making compounds. We'll get into using Lewis dot structures for that as well. Magnesium. So let me look at the electron configuration for mag. So I look, this is what I'll find for magnesium. So my electron configuration for magnesium, so at energy level 1, I'm going to have 2 electrons. Energy level 2, I'm going to have 8 electrons. Energy level 3, now I only have 2 electrons, right? So this bottom number is my number of valence electrons. So the number of valence electrons is going to be 2. And when I draw my Lewis dot structures, I'm going to have Mg, I'm going to have 1, 2 electrons with it. Last example, let me go to neon. So if I look up neon, I'll find this information. So my electron configuration is going to be at energy level 1. I'm going to have 2 electrons. Energy level 2, I'm going to have 8 electrons. So the number of valence electrons is going to be 8. And we'll come across as a bunch. 8 is going to be a magic number. 8 is very stable, and it's really important that it turns out if I have access to 8 electrons, then that's very stable. Neon is a very stable element. It doesn't form bonds with other things. So when I draw my Lewis dot structure, I'm going to put my 8 electrons. I'll go around first, put my 4, and then I'll start doubling them up. I'll end up having a total of 8 electrons. So the number of dots, each dot represents 1 electron. And I'm only showing those electrons at the outermost energy level. Anyway, I'm going to ask you to be able to do this. It's really important to be able to get this information off the periodic table. I'm not going to ask you to memorize any of it, but I need you to know how to use it. And I hope that's helpful. Talk to you soon. Bye.